Hello, Algebra 2ers. Today we're going to start the year off by learning a little bit more about functions and the vocabulary that goes along with them. For starters, let's talk about some functions we've dealt with in the past. In Algebra 1, we did a lot with the U shape or the parabola. We also did a lot with the linear functions or just the lines that you were writing or graphing. In Algebra 2, we have to expect that these functions are going to become a little bit more complex. So the images that we might deal with, the graphs we might deal with, are these functions that have continuous parabolas. There's multiple parabolas happening here. Or we might have functions that shoot straight down. So to figure out where we start, let's first off get a really good definition on what a function is. Let's determine what we are dealing with now in Algebra 2. So after today's lesson, we should be able to state the domain and range of a relation. We should be able to determine if a relation is a function. And we should be able to evaluate a function given a function notation. So let's dive forward and see what all this means. Again, going back to Algebra 1, we spent a lot of time making tables. You might have seen this machine that I have drawn on your page. We would end up giving you a set of values, input values. So if I were to give you this set of input values, you'd take every single value, you'd input it to the function, whatever the function might be. In this case, it's 2x plus 1, and some output would come out. So every single input you would put into the machine would produce at least one outcome. So 1 went in the machine and came out as a 3. 2 went in the machine and came out as a 5. So we had an input and we received an output. So in your notes, in your foldable, let's look at the definition of what the difference is between a relation and a function. If we look at a relation is a set of ordered pairs with a domain, which are your x values, and a range, which are your y values. Well, okay, so we would kind of think, well, isn't that just a function? Well, in order to be a function, it's a relation where each value, each domain, each x value is paired with exactly 1. Now, exactly 1 doesn't mean more than 1, and it doesn't mean less than 1. It means only one range value or y value. So every x pairs up with 1 and only one y value. Okay, so just for starters, let's take a look at this little pencil in the corner. Hint, hint, that pencil means we should probably be writing this slide of notes down in our notebook. Today you have a foldable. Not every day will you have a foldable to fill in, so let's make sure that we pay attention to when that pencil pops up on our screen so we're making sure we're taking good notes. So let's start with a couple examples. In these examples, we're asked to state the domain and range of the relation, and then after we do that, we're supposed to determine if it's a function. So the first example we're given is given in the form of a table. A table we should be pretty familiar with, but we have our x values listed in the left column and our y values listed in the right column. Now, these are just ordered pairs, 0, 2, 1, negative 1, 2, negative 4, 3, negative 7. So we could take all of those ordered pairs and plot them on a graph. But for right now, we're not asked to do so, so let's just find the domain and range. Thinking back to the definition of a domain. Domain is all of my x values, and range is all of my y values. So when we talk about writing domain and range, we're going to write it in that set notation with those squiggly lines. For domain, I'm going to start by labeling it D, and I'm going to list all of my x values. Every single one of them is going to be listed in my domain. So that's going to look like this. We have the D, the colon, and then 0, 1, 2, 3 inside those squiggly marks. Same thing goes for the y's. So range, instead of using a D, we're going to use an R. And again, we're going to list all of my y values. So that looks as such. But why didn't I list that 2 first? Why is negative 7 first? Because we want to list domain and range in values least to greatest. So here in my table, -7 was the lowest number. Yes, it's the lowest number in the picture, but it's also the least amount. So -7 means I'm -$7 in the hole, which we don't want. So you always want to go from least to greatest. So now that my domain and range are done, the second part of this example wants me to determine if it's a function. Thinking back about the definition of a function, that means every x has one and only one y. So let's look at this table. 0 goes to 2, 1 goes to -1, 2 goes to -4, and 3 goes to -7. All of my x values over here only have one y value. So would this be considered a function? Absolutely, it's a function. So let's try another example. Here, we're going to talk about a mapping diagram. The mapping diagram might be a little unfamiliar to some of us, but this is just very similar to a table, except the lines that we drew over here from 0 to 2 are already drawn in for us. So they're still listed in a table format. Your x is on the left, your y is on the right, but now the lines are drawn in for us. Again, we have to do the domain and range. Remember, domain, we start with the D, we put in the colon, and we list every single x value. So here we have 1, 2, 3, and 4. Okay, now on the y, or the range, again, we start with the R, and we list all of the values. But remember, the values have to be put in least to greatest. But we're dealing with letters, so how are we going to do that? Well, our alphabet has an order, right? We sing the ABCs for a reason. So again, we have to put those in order, B, C, D. So finally, let's decide if this one is a function. What are the rules for a function? Every x has exactly one y. So let's look. 1 goes to D, 2 goes to B, 3 goes to C, and 4 goes to C. Wait, so 3 and 4 both go to C? Yep, but looking here, 3 only goes to C and 4 only goes to C. Yes, they have the same output, but they don't have more than one. So every x still only has that one y. So this would still be a function. On the other hand, if we look at this mapping diagram, we'll start by doing the domain and range. So we'll start here, doing the domain as my x values, starting with that D, putting the colon and the squiggly lines, -8, -5, and 7. The range again is what values? Y values. So we'll put them in order, -6, 1, 2, and 3. So again, we have to check if this is a function. In order for it to be a function, it has to have only one y for every x. Every x can only have one y. So let's look here. -8 goes to -6. -8 goes to -1 as well. Right here, the two arrows going from my x to my y's should automatically indicate that this is not a function because there is one output and two outputs. You can only have one output for every input, only one y for every x. So this final diagram is not going to be a function. So now, what if the points are already graphed for us? Let's think about how we would determine if a function is a function. Thinking about those U-shapes, those parabolas, those straight lines we've drawn, or a circle on a graph, how do I determine if it's a function? Thinking back to Algebra 1, what did you do in Algebra 1 that helped you determine if it was a function? We have this vertical line test. So again, we notice the pencil over here, so let's get this written in our notes. Vertical line test, a relation is a function if a vertical line drawn through its graph passes through only one point. Now, an easy way to do the vertical line test is if you take a pencil and you hold it in your hand and you move it left to right over the graph that's drawn. If it touches your pencil more than once, it is not a function. Remember, more than once, it cannot be a function. So let's look at a couple examples using this tool we have. Would this graph be a function? So looking here at the graph, again, we're using that vertical line test because the points are already plotted for me. It's already on a graph. So now I just have to take my pencil, put it over my graph, and start moving it left to right. So left to right, we're moving it left to right. If I move it a little bit, no, not quite to my function yet. Move it again all the way over to my function. What do you notice? Well, before I moved it, we noticed there was a dot here and a dot here. So that means my pencil is touching two different spots of this function. Well, does that mean it's a function? Nope, because my pencil here cannot touch more than one point on my graph at any given time in order for this relation to be a function. So let's try another. Looking at this graph, again, since it's already graphed for me, let's use that vertical line test. Put your pencil over the screen if you need to. When I'm doing the vertical line test, again, remember we're going left to right. So taking this pencil and moving it left to right, making sure that it doesn't cross more than one spot on my pencil at any given time. So when I moved my pencil there, did it cross this function twice at any given point? Nope. So would this be a function? Absolutely, this would be a function. So let's talk about one where we maybe have a circular figure, or more so an oval than a circle here. Again, since it's graphed for me, let's just use that vertical line test. Let's place my pencil over this, move it again left to right, it's vertical, and see if it crosses my pencil more than once. Right here, not so much. Right here, uh-oh, I see two dots that it had crossed my pencil at those points. So what does that tell us? That this cannot be a function. It crossed my pencil twice, therefore I do not have a function. So now let's get into what function notation is. Often the function rules are written as y equals 3x plus 4. Now this is something we're really used to and we're going to kind of have to get out of the habit of. Algebra 1, you dealt a lot with the y. In Algebra 2, it's going to be mainly this function right here, this f parenthesis x parenthesis. Now, it's no different. It's the same exact function up here, but we just write it a little differently. F of x is what we call it. So the y is just replaced with the name of the function. So when we look forward, f right here, this f out front, is just the name of the function we're dealing with. We're going to get to graphs that have multiple functions on them. And we want to make sure we know exactly what function we're talking about. So the f, the letter outside of the parentheses, is always going to be the name of the function. Now, looking further, this x that's in parentheses, this is just telling us that we're inputting for an x, which is exactly what you guys were doing. This x right here, we knew that there was a value for x, but this notation tells me that I have that x value that needs to be inputted to the function f. So again, this side over here, our right-hand side, is still the mathematical rule. It's still our machine, if you want to call it that. And we're still inputting a value. We're still using our table, essentially. But this time, my label, my y, is no longer a y. It's f of x. That first function should tell me exactly what to input. So right here, with this f of x, like I said, it's no different. It's still that y value. And we say it, the value of f at x, or as I have been saying, f of x. So this is the function f with an input value of x. So why does this notation help me? Why does this f of x help me? When we look further, we're going to talk about evaluating. Like I said, this is the last thing we're going to learn today, how to evaluate functions. Previously, you had a y equals negative 3x plus 7. And if I told you to evaluate each at x equals negative 2, you would just substitute this negative 2 in for the x. Well, in this notation, we're taking the function f, and in my input value, since x is equal to negative 2, my input value is just going to be negative 2. Since I replaced an x up here when I had my y, when I was used to writing my y notation, when I replace that x up there, it still replaces the function notation as well. So f of -2 equals -3. Again, wherever I see an x, I'm going to plug in that -2. And every time I plug in numbers, I like to put parentheses in just so I know that something has changed. Something's different from the first equation, plus 7. So here, same function, now we just do order of operations. So again, just a reminder, order of operation is PEMDAS, right? Okay, so what comes first, multiplication or addition? Well, as we can see, our multiplication comes first, so -3 times -2 is 6 plus 7, and 6 plus 7 equals 13. So f of -2 equals 13. So my input was -2, my output was 13. If I wanted to rewrite this as an ordered pair, the x value I plugged in was -2. What I got out after plugging it in was 13. So my ordered pair here would be -2, 13. So going to the second example on this page, now I need to plug x is still -2. I need to evaluate both functions with x being -2. Again, my function here is g, but that input x equals, so since it equals, I can substitute it in, x equals -2. So wherever I see an x, I better be substituting in a -2. G of -2 equals, again, when I plug in, I like to use parentheses, -2 squared plus 2, since I plug in another x, plus 10. Use those parentheses to show that we changed it a little bit. So, order of operations. If I look back over here at PEMDAS, order of operations says I do parentheses first. Well, there's nothing in either parentheses for me to do. Next comes exponent. So -2 squared. -2 times -2 is a positive 4. Plus 2 times 2, -2, excuse me, plus 10. After exponents, the next thing would be multiplication and division. So I get 4 minus 2 times a -2 would be a -4 plus 10. Now I have addition and subtraction. Which one comes first? Trick question. Since they're on the same line in my PEMDAS, you do them from left to right. So 4 minus 4 would be 0, plus 10 would be 10. Again, this was g of -2. So the function g, I input that 2, and my output was 10. So if I were to write this as an ordered pair, I'd get -2, 10. The last couple of examples we have here are just written in a different form. We aren't given exactly what x equals. It's not written as x equals, but we still need to evaluate. So now remember, here is the function notation we're going to get used to. This is the name of my function, and this right here is what I input to my function. It's that x value, my input or my domain. So looking at f of -4, so I'm using the function f, that's the name. What is this -4? What's different between this right here and this right here? I'm missing an x. So that means this -4 here replaced my x. So when I go to my function, it should replace all the other x's in my function. So I should have f of -4 equals -3 times -4 plus 7. No more x's, since I didn't have x's over here, since I'm evaluating for what x is at -4, plugged it in for every other x in the function. So PEMDAS tells me to multiply first, so then I'd get -3 times a -4 gives me a positive 12 plus 7. 12 plus 7 is 19. Again, this is f of -4. This was my input. When I inputted -4, I got 19. So this 19, oops, wrote it again, would be my output. So writing that as an ordered pair, I'd get -4, 19. So this last example B, I'm going to have you to complete for class tomorrow. I will check your notes when you get to class, but thank you for being good listeners. I hope you took great notes.